NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello everyone, and a very pleasant evening to you wherever you may be. Welcome to another remote edition of our Von Karman series. I'm Brian White from JPL's Office of Communications and Education, and tonight we'll be discussing Venus, Earth's evil twin, or just misunderstood. A few quick reminders. We ask if any technical issues arise. We have had calls here in Southern California of rolling blackouts. We ask that you stick with us as we get them sorted out. We'll keep going as best as we can, and we also want you to be involved in this conversation. If you're joining us on YouTube or Facebook Live, you'll notice a chat window. Now, if you can't see the chat window, go ahead and refresh that page and it should be there. Ask questions and our hardworking social media team will bring them into our conversation throughout the night. And helping us out this evening is Lindsay McLaurin, Public Outreach Specialist. Hi, Lindsay.
Hello, Brian. Hello, everyone. I'm looking forward to fielding your questions tonight. So make sure you use the chat, and I'm excited to hear Sue speak.
Wonderful. Thank you, Lindsay. Thanks for joining us on your Thursday night. And folks, we want to remind you that this is your space program. There are a ton of NASA resources available online, but one in particular I'd like to point out tonight, and that's solarsystem.nasa.gov/planets/Venus, and that's going to be image number 2. Now, as you may have guessed, you can explore our whole solar system through this website, but after our talk, if you're thinking, I want to know more about our twin, head there and you'll uncover a whole mountain of information about the planet, galleries and images and videos, plus information about missions and notable explorers, which you can see down there bottom, include this evening's speaker. Now let's get to meet our speaker. If we go to image number 3, you're going to see a principal planetary scientist with JPL since 1992. She has worked on missions to both of our neighbors, Mars and Venus. Please welcome Rocky Planet Geoscientist, Dr. Sue Smrekar. Hiya, Sue.
Hey, hi, Brian. Hi, everyone. Thanks for having me to talk about my favorite planet.
Well, thank you for being with us and talking about your favorite planet. And that's a big question right now. Why are we talking about Venus tonight?
Venus is like this incredible cosmic accident. You know, there's all this primordial stuff floating around in our solar system, and planets form. None of the planets are more similar than Venus and Earth. No two moons, no two planets. It's just this crazy accident. These two bodies ended up so similar. They're both close to the sun. They're similar in size and composition. And, you know, on the flip side, there's the atmosphere that gives it the evil part, that sulfuric acid rain, the incredible surface temperature. You know, it's hard to get about 10 words into a description of Venus without hearing the word hell. But we really don't know how long it's had those surface conditions. And it actually could have been the first habitable planet in our solar system.
Well, let's talk about those similarities, and then we'll talk a little bit about that evil part of it. Let's go to image 4, and you can talk us through some of these similarities here a little bit.
Sure. So you see 3 green planets, Venus, Earth, and an imaginary exoplanet. You can see that Earth is just slightly larger than Venus. We know that the densities are very similar, which tells us they have a similar bulk composition. And we've even looked at some of the atmospheric composition, which tells us that Venus used to have a shallow ocean's worth of water at the surface. Now, we don't know when that surface water was lost, but we know that it very likely started out much more similar to the Earth than it is today. And, you know, that's super important because, if you're a space fan, you know that they've been finding hundreds and hundreds of planets around other stars. And, you know, we're really trying to find, Earth 2.0, right? The planet that is so much like our own planet, but around another star. And so to begin to, predict which of those more or less points of light that we or points of lack of light as they transit in front of stars, those exoplanets, which ones are likely to be like Earth? If we can't understand how these two twin planets evolved on different paths, we can't really predict are exoplanets going to be like Earth or not.
So that twin aspect is not only helpful for here on Earth, but also in discovering worlds beyond our system. Wonderful. Let's go to image 5, though. Let's talk a little bit about what makes this title so interesting, the evil part of this.
Right. So, the surface temperature is crazy hot. It's one more planet closer to the sun, and that would account for about 100 degrees Fahrenheit difference in the temperature. But in fact, it's the surface temperature is 460 Celsius, about 900 degrees Fahrenheit. So, it's the fact that it has this intense greenhouse atmosphere, 97% CO2, that makes the surface so hot. And that incredibly dense atmosphere is about, 90 bars, almost 100 times more dense than the Earth's atmosphere. So it's like being half a mile under the ocean. It's so the atmosphere, the air itself is so dense. So this is the place where the runaway greenhouse was first discovered. And, this is where the evil part comes from. The surface hot enough to melt lead.
Cool. I want to bring up our next image because we've talked about Venus before, at least in NASA's history. A big part of that we could see right here. But you've got a relationship with this mission also. This is Mariner 2, and it was the first successful mission to fly by another planet. What's your connection with Mariner 2?
Well, Mariner 2 was the first spacecraft that flew by another planet. It just so happens that was the, not only the start of the space age, but the year I was born.
So you've got a great connection. And also the picture we saw earlier, you were standing in front of Venus, Pennsylvania, right?
Right, where my father was born.
So you've long been related to this planet. Something you talked to me about when we were getting ready for this, there was a great analogy you had with Mars, and it kind of connects with Venus a little bit with these earlier missions, and why maybe Venus doesn't get talked about as much.
Yeah, I think there are a lot of parallels between Venus exploration and Mars exploration. In the very start of the space age, there were a ton of spacecrafts that explored Venus. And with Mars, there was also a lot of interest in Mars. But the first lander on another planetary surface was a Viking lander. And, people were very excited to try to test and see if there could be microbial life in the soil of Mars. So that's what the Viking lander was designed to do. But the answer came back negative. And so people were like, Mars is dead. It's boring. Forget about it. Similarly, the last spacecraft that explored the surface of Venus was an orbiter from NASA 30 years ago. And from that mission, a lot of people concluded that Venus was geologically dead. And so also not terribly interesting. But like with the Viking lander, in that intervening decades, that was back in the 70s, people realized that test that they did for life wasn't the best approach to actually look for evidence of past life. And so, of course, now we have this, extremely robust Mars program where they're sending spacecraft after spacecraft. And, now we have the Perseverance rover on its way to look for life because the science of looking for life has evolved. And similarly for Venus, what we've learned in the last 30 years has given us a completely different perspective on Venus. We no longer think it's geologically dead. We have good evidence to think it's active. And, we've learned a lot of other things about where volatiles come from, which is mostly from the interior rather than from comets. So we have a lot of reason to think there's still water in the inside and that it's geologically active.
That's very cool.
And it's time to go back.
It's time to go back. And I'm sure people already have questions about this. So we're going to bring Lindsay back in here and let's see what people are asking online.
Absolutely. So Rohit on Twitter would like to know, how would a rover be powered on the surface of Venus?
Oh, that's an excellent question. Yeah, it's very challenging because of those incredibly thick clouds and because of the super high surface temperature. So a lot of things that we would normally use just don't work. So people have really been investigating that and looking at things from, very, very low powered solar panels that would give kind of a trickle charge. And people even looked at, wind power, like flying, literally like flying a kite from the rover to try to generate power. And then there have been ideas to look at nuclear power as well, but there's really, that's very challenging at 900 degrees. So it's tough to operate for a long time on the surface, but it is being investigated and people are trying to move forward and come up with really innovative ways to make things last for a long time on the surface.
Very cool. What else we got, Lindsay?
Yeah, absolutely. So Mark on Facebook asked, is the high pressure of the atmosphere due to the extreme temperatures, or is it because there's a lot of atmosphere pushing down on Venus?
Yeah, so it's kind of both. The atmosphere is, it's not so much, thicker than our own atmosphere, but it's a lot more dense. And the more dense an atmosphere is, the hotter it's going to be at the surface. So, just like, we just had a Death Valley be 130 degrees. And one of the reasons is one of the hottest places, if not the hottest places on the surface of the planet, is because it's so low. So the higher pressure increases the temperature as well. So it's kind of a combination of those things.
Cool. Lindsay, I think we got time for one more question before we move on.
Amal on Facebook asks, what is the reason behind the acid rain on Venus?
Well, the clouds on Venus are largely sulfuric acid. And, the sulfur in the atmosphere, we think comes from volcanoes. So that's one of the key components of the atmospheric composition. And at that pressure and temperature that you get on Venus, that's the one of the dominant parts of the cloud composition. There is some water as well. And, the temperature, the volcanic outgassing, everything is just right to create sulfuric acid rain. It does actually get to the surface, though, because the surface is so hot. It just kind of falls, but it evaporates before it hits the ground. Sorry.
Well, no, that's interesting, and that's actually a good segue. Because if Venus is like Earth, what are these smaller similarities that you would want to study? And a lot of good questions. We're talking about rain, but what are these connections and things that we actually can look at and learn about?
Yeah. So, the surface is, very interesting, of course. But it's only perhaps relatively recently that it's attained this super intense greenhouse, and it's superficial, right? Atmospheres can change, but the surface of the planet is where we really get to the incredible analogies with things going on the Earth. Like I said, it's similar bulk composition, similar size, and so that really means it has a similar engine, if you will, to drive activity on the planet and in the interior and in the atmosphere. So, on Earth, on any rocky body, you have a ton of heat. It's like I said, an engine. There's radiogenic heat. There's heat from cooling, and on Earth, the system of plate tectonics is what happens at the surface to let that heat come out. On continents, we have all these plate boundaries, mountains collide where plates collide. San Andreas slips past each other very close to here. And then there are plates that sink into the mantle. One plate subducts underneath the other. And this system of plate tectonics is, just the primary force that shapes the surface of our planet. It's had a huge impact on the overall climate, evolution, and maybe even the habitability of Earth. And before we had this spacecraft Magellan, everyone thought that Venus would have plate tectonics. But it turns out it doesn't seem to have plate tectonics, although it seems to have the conditions which we think lead to plate tectonics. So in particular, we think it has this process subduction, and it's super interesting because that early in Earth's evolution, this whole system got set up, and billions of years ago on Earth, the lithosphere was hotter, the outer part was hotter, and that makes it potentially easier to start this whole process. We think that's maybe going on Venus today, but we have so many questions about how it actually begins for the Earth. On Earth, we think it happened billions of years ago, and we have very little evidence, concrete rocks, data from that time period. So Venus is a place we can go and potentially learn about the very early evolution of the Earth.
Fantastic to have, and it's right there. It's right next door. Yeah. Well, something I do want to talk about. So there's plate tectonics. Not yet, but the subduction is there, or the theory of subduction is there. But let's talk about volcanism. Let's talk about volcanoes. And if we go to the video, number 7, that gives us a good look at some of this too.
Sure, yeah. So this is some data from Magellan, and you're seeing topography, and you're giving it the volcanic shape, and you're seeing the bright zones are rough lava flows. So it's reflecting the radar waves back. So this is one of the prominent volcanoes, and we think it's been recently active. This color data that you're seeing now, the red and hot colors are areas where we think there has been relatively recent volcanism from looking at the first order changes in the surface composition. We think that lava erupted relatively recently and hasn't really changed its composition to interact with the atmosphere yet. So it's one of the handful of volcanoes that was covered with this data, and we think there are many more volcanoes like this that could be active on the surface.
If we go to image 11, actually, we've got a bunch of other great images from this. And how did Magellan really get these? How did we get what we're looking at here?
Yeah, so Venus has got this dense cloud layer. So we have to use radar to transmit those long wavelength signals to the surface. And those radar waves bounce back. And so the areas that you're looking at here that are bright, those are rough surfaces, like an lava surface. If you've ever seen images of very rough lava flows in Hawaii, these are really rough lava flows that have the bright reflections in radar. But there's just all kinds of crazy volcanic features all over the surface of Venus. Like this volcano on the right, it's like 9 kilometers tall, so like 5 miles tall. It's enormous.
That's, oof. I know there's going to be some good questions about the volcanism. There usually is from particular students out there. But I want to actually take another look at image 10, actually, and come back to subduction, which you were talking about before. But this is an artist image of it.
Yeah, this is an artist image. It's based on actual data for Venus, but it is an artist image. And you can see that kind of a curved trough in the foreground, and with the volcano in the center. And we think this is how subduction actually starts, where you have hot material coming up in a plume from inside the planet, just like we have in Hawaii, which pushes the topography up, and it can break through that strong outer lithosphere. The volcanism that forms can push that broken lithosphere downward. So what you're seeing there is that the volcanism is creating the subduction, and the lithosphere is just starting to fold down into that trough, and the volcanoes are continuing to form new crust there. That's our interpretation, and it's depicted very dramatically here in this artist's conception.
Very cool. It seems like we do have a volcano question that we'll bring in from online, and then we'll talk about a mission that's close to your heart. Lindsay, what do
So,
we got?
yeah. So Lainey on Facebook is curious to know, can scientists or engineers learn anything from the Earth geologists who study volcanoes on ways to manage science through extreme heat?
Well, we can certainly learn a lot about processes on Earth from both studying Venus and studying Earth. Now, in terms of the extreme temperature, sure, there are lots of engineering applications on the Earth for devices that have to work at very high temperature. We are trying to apply lessons that people are developing for very high temperature electronics, to perhaps operate sensors inside a nuclear reactor, for example, to take that kind of technology to the surface of the Earth, surface of Venus, rather. And also, people use devices that go down inside our planet. They did drill holes to look at how much heat's coming out of our planet, or to look for oil, or there are a lot of reasons that people drill into the Earth, and so those are also engineering approaches that we take from Earth to Venus. But also, we have learned a lot of different things about volcanic processes. For example, we want to know what's coming out of the volcanic gases. And people who are studying the atmosphere of Venus were actually the ones that discovered the ozone hole on the Earth, because they were looking for similar kinds of chemical processes in the atmosphere of the Earth. So, there are both scientific and engineering lessons that both planets have for each other.
Very cool. I think there's one more volcano question, and then we'll talk about that mission.
Cool.
Yeah, so folks are really excited about the volcanoes. So Callie on Facebook wants to know, how are there volcanoes without plate tectonics?
Yeah, well, it's true that a lot of the volcanoes on the Earth are a result of plate tectonics, and in particular subduction. Like the Ring of Fire that you hear about around the Pacific, where there's all those giant volcanoes that edge the Pacific Ocean. Well, most of those are actually a result of subduction, and that's where. So one plate is being pushed underneath the other, and when that downgoing plate melts, those volcanoes are created. And that's basically that process that we were looking at in that previous image. So, maybe at least a few of the volcanoes on Venus may be related to subduction. But in addition, there are other kinds of volcanoes, like Iceland, like Hawaii, and those are formed when there's hot material rising up from the core mantle boundary and creating volcanism at the surface. So even though a lot of volcanoes on Earth are related to plate tectonics, we do have, even on Earth, we have volcanoes that are not directly related to plate tectonics. And basically, you just have to have a mantle that's hot enough to melt, which could be the case for Venus, which can allow volcanism as well.
Very cool. You've asked all these great questions and talking about all these wonderful things that we can study. I imagine there are some questions right now. Are we going to go study Venus at any point?
I certainly hope so. Yeah, there's a lot of different Venus missions are in competition to try to go back to Venus in the next to get launched, say, in the next 5 or 6 years. In the U.S., in Europe, and other countries, there are a lot of people, a lot of spacefaring nations are interested in going back to Venus suddenly. And yeah, the one that's closest to my heart is one that we've been working on for some time now, designed to answer some of the really fundamental questions about Venus. About what processes are active, what volcanoes are active, can we see active faulting on the surface? Is there still water inside the planet that's being released by a volcano? So lots of fundamental questions we'd like to answer about Venus.
And that mission is called, if we go to image number 12, you could take a good look at it right here. It's called Veritas, right? Truth.
Yeah. It's a long acronym, but it's designed to study the surface using radar. We would get orders of magnitude better resolution topography and radar imaging than we've had in the past. And, we're trying to understand how this big hot planet like Venus can operate if it doesn't have plate tectonics. Does it have some other system that we don't have the data to actually understand at this point? We've gone back to Mars, time and again with like better and better resolution data. And every time we go back with better resolution, we see processes that we just didn't anticipate. And so, I have a whole, suite of ideas that I think will, processes I think we'll see, questions that we want to answer. But when you get like just incredibly better data, you're likely to just find things you never even imagined. So, we'll do things like look for chemical fingerprints of water in rocks. Like, as I said, we don't know how long ago that ocean was, boiled off essentially, but we think we could have the ability to see with a spectrometer that sees through these clouds, the fingerprint of past water. So that's a really big question. And just understanding how overall the geology in Venus works. We just really don't have the resolution right now to understand the planet as a whole.
The fingerprint of past water, that's a great sentiment right there. In just a second, we're going to open it up to get some more questions in. But I do want to give you one moment, because this is your favorite planet. One last kind of moment of what is it that you love about it? Why Venus?
Yeah, I've continued to study Venus for decades, despite the lack of data. And that's because it is such an incredible laboratory for understanding our home planet, for understanding rocky planets, for really understanding the evolution of planets. As we've learned more and more about the Earth, all those lessons we can take and put in the context of Venus to understand how it formed. For example, 30 years ago, we thought that most of the planet's water comes from comets that come into the planet late. And what we've learned since then is that most of Earth's water actually is a result of the original, rocky bits of planet, planetesimals that it formed from, and that it's the process of volcanism that primarily releases that water from the interior to form our atmosphere and to form our oceans. And, we think that Venus may have actually more water still locked in the interior than the Earth. So, as we learn more about our solar system, how rocky planets evolve, we have this chance to use Venus, Earth's twin, as a laboratory to understand overall how processes work. We know so much about the Earth, how the geology works here, but it's only one planet, and we have this chance to study a planet that's almost the same size, should have a lot of activity. Venus has a very young surface compared to like Mars and Mercury and so forth. Those planetary surfaces are billions and billions of years old. Venus is less than 1 billion years old, in some ways very comparable to the Earth. And the other great thing about it that makes it a geologist's dream planet is that there's hardly any erosion. Today there's no water. That dense atmosphere doesn't erode the rock very rapidly. On Earth, most of the erosion occurs from water. And so, tons of processes get buried by erosion, by sediments being deposited on it. So, the surface that we look at on the Earth, for the most part, it's not the primary surface that was created in the original geology. On Venus, it's the original geology is sitting right there at the surface. So we have a chance to, look at that processes. Like I work with a terrestrial geologist who studies subduction zones on the Earth, and she's, very, frustrated by the fact that she can't see the faults in most subduction zones because of all the sediment. On Venus, we go look at these possible subduction zones. You can see the fractures exposed right at the surface. So, there's just so many ways that Venus is an incredible laboratory to understand processes that are important on Earth, and maybe a lot of other places. And I guess the ultimate question for me is why is Earth the only place with plate tectonics? Are we really unique? And if so, why? That's kind of the question I would love to answer.
It's all right there. Let's go take a look at it. Let's open it up for a few minutes of questions from our live audience. They've been great questions so far. So, Lindsay, what else we got?
Yeah, so a really great question that we have from Jonathan on Facebook is, what are the major complexities for keeping a camera or other instruments functioning on the surface of Venus?
Yeah, the major problem is the temperature. That's the first problem that'll get to you. The landers that have gone to the surface successfully so far have basically been like diving bells, these enormous, steel vacuum chambers. And they are super well insulated. And so, it actually takes, the atmosphere is so dense, it actually takes like an hour to fall through the surface from coming in extremely fast, and then they slow down in the atmosphere, fall to the surface, and they really only last a few hours. And in those few hours, because of that incredible insulation, they actually cook from the inside out. So they start off cool, but with the insulation, they just begin to cook. And then the next problem is the sulfuric acid. It's extremely corrosive, and in fact, the carbon dioxide at the surface, the CO2, is in a state that's called supercritical. So it has some of the properties of a gas and some of the properties of a liquid. And supercritical CO2 is actually used as an industrial solvent. So those are some of the first order problems. Then you have to have energy.
So Gary on Facebook, Gary on Facebook wants to know, what would it take to determine how long Venus has been in its current condition, and how long ago the ocean disappeared, and how could that be done?
Yeah, well, there are a lot of different measurements we'd like to make to begin to answer that question. What we would like to do with Veritas is, as I said, look for these chemical fingerprints of water. There are these particular types of geologic features that we think are analogous to Earth's continents, which, basically continents, again, they're kind of enigmatic because they started to form billions of years ago. But most people think that they form when basalt, the primary crust that the planet forms, like the oceanic crust on the Earth, that melts in the presence of water and creates a new type of rock, the kind of granite rocks that we see in continents. So that's the kind of rock that we're looking for, to see if there's evidence of the basalt, the volcanic rock, melting in the presence of water. And we can have, with the better data, we can have hope to have a pretty good idea of how old those rocks are. So we think we'll be able to discover more impacts craters in that type of terrain that is used to date the surface of rocky bodies. So that's the thing we're trying to do with Veritas. You can also study the composition of the atmosphere in greater detail. You can use isotopes to try to determine how water and other volatiles have formed over time. Those are kind of divided into different time periods, and so some of those time periods can also help to pin down when that ocean might have been lost.
So Jeb on Facebook asked, would a mission to study the upper atmosphere of Venus more closely be a priority in the future, and what would you hope to discover there?
Yeah, well, there's actually a Japanese mission currently at Venus, and it is studying the atmosphere, including the upper atmosphere. And there was a European mission until about 5 or 6 years ago, and that mission was also studying the atmosphere of Venus, including the upper atmosphere. And one of the very interesting things that has come out of those two atmospheric oriented orbiters is the fact that oxygen is being lost from the atmosphere, the upper atmosphere, at a similar rate on Venus, Earth, and Mars, which is just crazy. No one would have predicted that. We think that until recently, we thought, okay, Earth has a magnetic field, and that helps shield our upper atmosphere from the solar wind. So the solar wind comes in and peels off the outer atmosphere, and including this oxygen that's being lost. So, so apparently neither the size of the planet nor the magnetic field are nearly as important as we thought. So, was a very interesting discovery that people would like to follow up on, I'm sure.
All right, we got time for one last question.
And Sue, I think this is my favorite question that anyone ever asks any of us at NASA. Is LaShonda on Facebook wants to know, do you look for life under the surface of planets?
Yeah, it depends on which planet you go to. Venus, you definitely would not look for present day life near the surface, and probably because of that present day high temperature, it's likely that you might destroy any evidence of microbes that might have been there in the past. But people are interested in trying to look for microbes in the atmosphere of Venus. That cloud deck that's, it's about 60 kilometers, say about 40 miles up. The temperature and pressure in the cloud deck is actually similar to the surface of the Earth. So in theory, you could have microbes in the clouds of Venus. People are interested in trying to study that. But other places, you do want to go beneath the surface, like Mars. It has it doesn't have a very thick atmosphere, and you get a lot of radiation at the surface. And so, it's better to go a little bit under the surface to try to look for evidence of past life. So it really depends on what body you're going to, where the best place to look for life might be, or evidence of past life. Let's say, so certainly when we're talking about Mars, who knows? Who knows for Venus?
Very cool. That's all the time we have for this evening. But before we go, another way you at home can keep exploring Venus is if you go to eyes.nasa.gov. And if we go to image number 14, you can kind of see a little bit of what they have, what they can show you on here. NASA Eyes will be a major part of next month's talk, Visualizing Space Exploration, AR, VR, and Emerging Tech. Now, before we go, I would like to thank our speaker, Dr. Sue Smrekar, our co-host, Lindsay McLaurin, and everyone behind the scenes that makes these talks possible. And a final thank you to you, the audience. Thank you for joining us on this Thursday evening. Stay safe, stay kind, and we'll see you next month.